My name is Sumit Mohanty, and alongside my paronyms Christoph Yunis and Jakub Sikorski, I welcome you all to my doctoral defense. Now, before introducing my topic of research, I would like to talk about a science fiction movie from the 60s. In the year 1966, a movie Fantastic Voyage depicted surgeons shrunk to the size of red blood cells and deployed inside a human body to perform surgeries. Now, this whimsical concept revolutionized microsystem technologies to design and create robots that are less than a millimeter small and could potentially handle clinical tasks that large-scale clinical instruments cannot. And this was the ideation of the term microrobots. But the bigger question is, can we realize these microrobots using existing clinical standards? Well, before that, we ask ourselves some basic questions, like how can we build such tiny robots? We borrow some inspiration from the semiconductor industry that allows us to fabricate tiny chips in your cell phones that are roughly of the same size as these microrobots. Next important question is, how do we see such tiny robots, and that too inside the human body, where microscopes or cameras cannot enter? Fortunately, the clinical standards also allow us to use imaging systems such as MRI and ultrasound to see tiny features inside the human body, which are roughly the size of these microrobots. But most importantly, how can we move such tiny robots? Robots that are barely a millimeter small? And clearly, like putting electrical wirings or batteries are not an option, right? This is where we use some physical and chemical principles that allow us to exert indirect forces on these microrobots so that they can be moved at such scales. Now, this forms a segue to the previous question, that how about we use the physical principles that are already being used in clinical technologies to move these microrobots? And this forms the main crux of my thesis. In my work, I've combined magnetism and acoustics to power these microrobots, and finally use these two technologies together to realize what we call magneto-acoustic microrobots. I would like to start with the magnetic actuation part first. The simplest and the most established manner in which magnetism can be used to power microrobots is by applying rotating magnetic fields, which allow these microrobots to constantly align with them and thus swim. In this particular instance, these arrow-shaped microrobots have the magnetic arrows that constantly align themselves to magnetic torques, and this allows them to swim in water. Not just that, aside from the swimming behavior, they also hold the ability to go back and forth as we apply the magnetic field in a conical fashion. This unique property of our microrobots enabled us to address the first research question of my thesis, that how can we have magnetic microrobots with exactly the same magnetic properties, but move differently with the same magnetic field? And this unique property allowed us to use multiple microrobots that actually move differently under the same common and easy to apply magnetic fields. Despite the ease and convenience of magnetic actuation, it comes with certain intrinsic limitations. First of all, it requires the microrobot itself to be magnetic, and it uses heavy and bulky electromagnetic coils that can also dissipate heat and interfere with other instruments. These limitations lead us to the other viable option, which is acoustic actuation. And acoustic actuation can be applied in a wide variety of manners that allow us to manipulate objects at micro and nanoscale. We classify these technologies broadly in two categories. The first one being acoustic tweezers, which are composed of a set of devices that allow us to carry microrobots, just like a payload, and deploy them over long distances in centimeter scale. While the other technology deals with acoustic micromotors, which consists of acoustically active elements that enable microrobots to move by themselves. The former of these technologies enabled us to answer the second research question of my thesis, which is what kind of acoustic tweezers or acoustically powered devices can we make to move these microrobots along the surfaces and in the bulk of the medium. The first of this device is a 2D acoustic tweezer, which consists of a microfluidic channel that contains certain protrusions which vibrate when they are excited with sound waves. And as you can see, this vibration creates a flow through the microfluidic channel. This flow in turn can help us transport drugs, microparticles, or even microrobots through these microchannels. Such kind of technologies to transport microparticles in a contactless fashion is already in use in various microfluidic diagnostic platforms, such as the RT-PCR kits that you use, or the commonly available pregnancy test. The other kind of tweezer that we investigated here consists of an array of ultrasonic transducers that are compactly arranged to trap and maneuver microparticles or microrobots inside water. This compact array allows us to be easily interface it to large-scale robots and move these payload of microparticles across large distances. The application of these kind of tweezers is prevalent in ultrasound-based therapy, which is currently being used to remove tiny kidney stones from your body, which now can be done in a contactless fashion. While these two acoustic tweezers can carry or maneuver microrobots over large distances, we still desire these microrobots to be autonomous in order to be able to move by themselves and perform tasks so that they are useful to us. This enabled us to investigate the third research question of my thesis, where we use bubbles as vibrating motors to enable different kinds of motion in our microrobots. We begin with very simple arrangements of these acoustic vibratory elements, such as a circular or a helical arrangement, where these vibrating bubbles enable rotational motion in our microrobots. And the third category employs an array of these bubbles linearly arranged, which resembles the microfluidic tweezer I showed you earlier, but inside the body of a microrobot. And this allowed us to create a microrobot that could drive itself by an induced acoustic flow. This flow-driven microrobot finally led us to the final research question of my thesis, that can we use these acoustically powered bubbles and the magnetic steering as a common mechanism to drive microrobots? In this particular case, we functionalized these flow-driven microrobots with magnetic nanofilms that allow them to be steered under uniform magnetic fields. As you can see, they describe the letters S, R, and L, which stand for Surgical Robotics Lab. So I've shown you all these different technologies, but how do they come together? How do they stitch together into a common surgical application? Well, we envision a future where acoustic tweezers can be used to carry a bunch of microrobots through various pathways in the body and can deploy them to a specific surgical site, where they can be further imaged using clinical ultrasound, which is a technology already complementary to acoustic actuation. And finally, once at the surgical site, these microrobots then can be deployed with the magneto-acoustic actuation of the bubbles to perform surgical tasks like clearing debris or delivering drugs. But putting all these things together almost sounds like science fiction, right? Well, this whole field of research started with a fictional movie, and that's the thought I would like you all to go home tonight. Thank you all for your attention.